Hi, and welcome to this presentation on OpenFlow on the Cisco ASR 9000. My name is Kashish Golani, and I am a systems engineer in the Customer Proof of Concept Labs in London. There is a lot of hype in the networking industry around SDN. Quite often we hear terms like NFE, OpenFlow, ESP, EPN. So the purpose of this presentation is to demystify some of those terms and also to present to you the current capabilities of OpenFlow on the Cisco ASR 9000 platform. So what exactly is OpenFlow? According to ONF, which is the Open Networking Foundation, OpenFlow is an open standard to deploy innovative protocols in the production network. So what does that really mean? Well, it just provides a standardized hook that allows researchers to run experiments without requiring vendors to expose their internal workings of the network device. Well, that sounds really cool, but how exactly does that work? In order to appreciate the concept of OpenFlow, we need to first understand how routers and switches operate. Typically, the fast forwarding path, which is the data plane, and the high-level routing decision, that is the control plane, they occur on the same device in any networking platform. On an OpenFlow switch, however, these two are separate. The data plane portion will still reside on your device, while the high-level routing decision is moved to a separate controller, which is typically on any standard server. The OpenFlow switch and the controller, they communicate via a secure OpenFlow protocol. So now let's talk about this OpenFlow table. What exactly is a table, OpenFlow table? So in the data part of an OpenFlow switch, it presents a clean flow table wherein each flow table entry contains a set of fields to match on. This could either be the layer 3 source address, a layer 2 source address, a layer 2 destination address, a VLAN tag, whatever. And once the packet matches on those fields, an action that needs to be taken on that. That action could be either to send it out a particular port, to modify a particular field, or to drop the packet. So what happens when the OpenFlow switch receives a packet? So if it receives a packet that it has never seen before, for which it has no matching flow entries, the OpenFlow switch will send this packet to the controller. The controller will make a decision on how to handle the packet. It can decide to either drop it or it can add a flow entry directly to the switch, and that can tell the switch what to do when it receives similar packets in the future. So now that you kind of understand what OpenFlow is all about, let's discuss how the OpenFlow switching has been incorporated on the Cisco ASR 9000 platform. The current software release, which is the XR512, has support for OpenFlow, and it can connect to both OpenFlow 1 and 1.0 and 1.3 controllers. From the ASR 9000 perspective, this OpenFlow is just an application which runs natively in the iOS XR on top of 1PK. So what is 1PK? 1PK is basically stands for One Platform Kit. It is a flexible development environment that supports any programming language. It is built right into the guts of the operating system of all Cisco platforms, and it lets you communicate to the 1PK presentation layer, supporting the applications that can be written in either C, Java, or Python. Because this 1PK API is consistent, the application can be written once and then it can be deployed on any Cisco switch or router. So this OpenFlow agent runs on the RSP, and it is responsible to connect to an external OpenFlow controller. And what it does is it converts these OpenFlow messages to corresponding 1PK APIs. The reason why Cisco is using 1PK is because it gives a common infrastructure to support all SDN related features. So we already have discussed about an OpenFlow table. It essentially is a table consisting of a set of flows. Each flow will have a set of match and a set of matches that will match against and a set of actions that you need to take. In traditional networking, we classify the traffic using class maps and then apply the class map to a set of targets using policy map. Similarly, in OpenFlow, you have a table type depending on the criteria of your matches. However, this is applied in ingress direction only. Hence, your OpenFlow matches and actions are applied for incoming traffic only. So you can see that there are 4 different flow tables on the Cisco ASR 9000. If you want to match on layer 2 headers and you want to perform certain layer 2 actions, you need to define a layer 2 only table. If you want to match on layer 2 and layer 3 IPv4 or IPv6 headers and you want to take actions on layer 2 only, you need to define a layer 2 and layer 3 type of switch, a table. If you want to match on layer 3 IPv4 and you want to take actions on layer 3 IPv4 headers, you define a layer 3, layer 4 table. And if you want to support layer 2 and layer 3 IPv4 or v6 header and you want to take actions on layer 3 IPv4 or IPv6, you need to define a layer 3 dual stack table. Cisco has added support for some extra features on the ASR 9000. You have the set next hop, which could be either an IPv4 or an IPv6 next hop that can be used to redirect your IPv4 or v6 traffic to a specified next hop address instead of using your destination address in the packet. This provides ACL-based forwarding kind of functionality using OpenFlow. The IPv4 next hop address can be only applied to a layer 3, layer 4 or a layer 3 dual stack switch. The next bit is your FC ID, set forward class ID. This particular Cisco extension can be used to support policy-based tunnel selection functionality using OpenFlow. Apart from these 3 set actions, there is a NetFlow extension that is added by Cisco to enable or disable the NetFlow feature on an interface. Let's talk about some hardware support. Currently, there is support on physical interfaces like any GIGI, 10 GIGI or 100 GIGI, physical or sub interfaces. There is support for bundled interfaces as well as bundled sub interfaces. And BVI support is only added if you determine the flow table to be a layer 3, layer 4 or a layer 3 dual stack type. There is only support for pseudo-wire head-end sub-interfaces. So traditional pseudo-wire type of output interfaces is not supported. And only Typhoon line cards are supported for OpenFlow. You can have any chassis, so any 9000 chassis or any 9K chassis is supported. However, there is no support for a lot of type of interfaces like satellite. Satellite interfaces has no support for OpenFlow. The GRE interfaces and tunnel TE interfaces have no support. If your device is in a cluster, you cannot enable OpenFlow. And you cannot have the incoming interface on a Trident or a SIP 700 line card. In terms of scale, which is very important, as on the XR511, we do support 16 OpenFlow switches and 50,000 flows per system. This scale is limited to NP, so depending for each NP on the line card, you can support 50K flows. So the total scale of the line card will depend on the number of NPs on that line card. So that's great. Now that we understand a little bit about OpenFlow, let's talk about use cases. So the first use case that we can demonstrate in the CPOC lab is the layer 3 IP backbone use case. So you can, as you can see in this diagram, you have 3 different flows from 3 different sites connected to PE1, which are trying to send 350 megs of traffic each to PE3. There are 3 different servers behind your PE2. You have a video server, a web server, and an FTP server. They are residing in different VLANs. And the different flows are which are flow 1, flow 3, where the different sites are trying to send traffic to these servers. They are with 350 meg each. All of this traffic is going to take the shortest path across from PE1 to PE2. This is going to depend on the IGP, so that depending on the shortest IGP path, the traffic is going to take that path to go from PE1 to PE2. The bandwidth since in this case the bandwidth is only limited to 1 gig, this path is going to quickly get congested. So what is the solution? Well, one thing that you can do is you can manipulate the IGB cost so that you can change the path of the 3 flows. However, that would cause the path to change for all the flows. There is if that would not really solve your problem. So what does OpenFlow do is it gives you a very neat solution. With OpenFlow, you can change the path depending not only on the IP destination address, but on other criteria as well. So as you can see here, you can program the flow such that you can apply certain rules from the controller so that you can just redirect traffic from a particular source address to a particular destination address. So site 1 sending to video server can use the path to the other, and you could have another rule wherein you can say that site 2 traffic going to the web server needs to take path 1, and site 3 traffic going to the FTP server needs to take path 3. So that would effectively cause you to send traffic on different paths depending on the source and the destination address of the flow. In that way, you are able to efficiently utilize the bandwidth by redirecting the traffic appropriately. This is the demo that we've set up with, in the lab. We've got 4 different ASR 9000 devices, and we've got the POX controller that is talking to the controller that is talking to our PE4 device, and which is used to program the flows accordingly and redirect the traffic from port M to port N on different links depending on the source and the destination address. Let's talk about the next use case. This is the layer 2 enterprise data center use case. Now the enterprise data center will need to perform data backup to multiple other backup sites based on the traffic flow. The main data center is in VLAN 100 and the backup sites are in VLAN 1000, 1001 and 1002. These sites are interconnected using layer 2 VPN. In this topology, if the customer wants to selectively determine the backup traffic destination, then he or she will need to send them in separate VLANs. So what does OpenFlow do? OpenFlow can give you a very neat solution. With OpenFlow, you can match on any layer 2 header fields and appropriately steer the traffic. So in this case, what we could do is we could take the priority bits. So we could match on the incoming VLAN and the priority and steer the traffic to go on a particular layer 2 interconnect. And if you want, you can also rewrite the VLAN. So from the controller, you can put in certain rules. The rule number 1 could be that traffic coming in from the enterprise data center on VLAN 100 with a toss value of 1 should be steered towards the layer 2 interconnect 1 going towards PE2, and the VLAN should be rewritten as 1000. You could have another rule where you steer the traffic coming in from the enterprise data center on VLAN 100 with a toss value of 2 to be steered to the layer 2 interconnect 2 going towards PE3 and the VLAN to be rewritten as 1002. So similarly, there are a lot of rules that you can apply and you can match the traffic on the layer 2 header fields and appropriately steer the traffic to the different interconnects, layer 2 interconnects that you want. This is the setup that we have in the CPOC labs to demonstrate this use case. For this particular implementation, we are using the Open Daylight controller, which is talking on TCP port 6633 to the PE4 device. The same device is used for both the use cases, so we can even demonstrate how you can have two different controllers talking to the PE switch. So we will have both the POX controller and the Open Daylight controller talking to this particular device. So I hope you get a better understanding of what OpenFlow can do for you and your network, and gives you a certain idea of how you can play around and work more with this feature. If you want to see OpenFlow in action, please come to CPOC. We are geographically located everywhere around the world. This particular demo is in our London labs, so you can come here and get a feel of this demonstration and see it live in action. I hope you've enjoyed this session. Thanks for listening, and do subscribe to the Cisco CPOC YouTube channel for more interesting videos on new Cisco technologies. Thank you.